I'm Kohei Yoshida at the University of Electrocommunications, Japan. Today, I'm going to talk about analyzing performance and power exchange variation among NVIDIA GPU. As we reach the exascale era of computing, power consumption is becoming a major problem in the operation of modern supercomputing systems. In particular, Figure 1 shows that power consumption of processing units such as CPU and GPU account for about 60% of the overall power consumption of supercomputers. Thus, it's important to understand the performance and the power efficiency characteristics of these units so that their usage can be designed to reduce power consumption. In this context, many researchers have focused on the performance and power efficiency variation in compute nodes. A typical supercomputer consists of identical compute nodes in the same stock-keeping unit. It's assumed that these nodes have identical performance and power efficiency characteristics for a given application. However, the compute node used in a production system often exhibit wide variation in performance and power efficiency because of manufacturing viability. For example, another method shows that the power consumption of CPUs in the H8K supercomputer varied by 30%. Based on this observation, variational power management techniques such as variational job scheduler and power capping have been developed to increase the power efficiency and or performance of power-constrained supercomputing systems. In contrast to CPU, the performance and the power efficiency variation of GPU haven't been extensively studied, so many current supercomputers use CPU as an accelerator for special applications. To the best of our knowledge, there is only one report of such variation on GPUs in a production system. In their paper, the authors execute a real HPC application up to 196 NVIDIA V100 GPU with power and frequency capping. The impact of manufacturing viability on GPU is expected to depend on types of application running and the generation of GPUs, similar to the impact of manufacturing viability on CPUs. However, no previous study has investigated how the application type and GPU generation affect the performance and power efficiency variation of GPUs in the load capping scenario. In this paper, we present the first two evaluation of the performance and the power efficiency variation that can be expected in GPUs. We executed 48 CUDA kernel on 856 devices selected from three generations of NVIDIA GPUs, B100, V100, and A100, and collected 1.6 M plus performance and power profile from the executions. In contrast to the previous study, all our experiments were performed without power or frequency capping. We carefully analyzed this profile in view of the kernel type and GPU generation to determine the impact on performance and power efficiency variations. The experimental systems considered in this study are summarized in Table 1. We used the 3.0, flow type 2, and Wisteria-A system, each of which has a different type of GPU. As shown in Table 1, we used different number of GPU for each supercomputer in our experiments. This is because the maximum number of nodes available for a job differs in the experimental systems. SMART 3.0 is a GPU-based supercomputing system deployed at DI Tech since September 2017. It consists of 540 compute nodes, each having 4 Tesla P100 GPU. The peak performance of SMART 3.0 is 12.2 pflops. We use 256 GPUs selected randomly from the total of 2,160 GPU. Flow type 2 is one of the three subsystems of the supercomputer at Nagoya University, which started operating in July 2020. It's composed of 221 compute nodes, each having 4 NVIDIA V100 GPU. The peak performance of flow type 2 is 7.5 pflops. We use 240 GPUs selected randomly from the total of 884 GPUs. Wisteria-A is a subsystem of the Wisteria-BX01 supercomputer at the University of Tokyo, which started operation in August 2021. It consists of 45 compute nodes, each having 8 NVIDIA A100 CPU. The peak performance of Wisteria-A is 7.2 pflops. We use all 316 GPU in our experiment. We use more than 240 GPU in each of three systems, and this exceeds the number used in the previous study. The architectural differences between the GPU used in Inspiron 3.0, Flow Type 2, and Wisteria are summarized in Table 2. The Tesla P100 GPU, which is based on the Pascal architecture, was announced in April 2016. The peak FP32 performance is 10.6 TFLOPS. The thermal design power TDP is 300 watt. The NVIDIA V100 GPU adopts the board architecture and was announced in May 2017. The peak FP32 performance is 15.7 TFLOPS. The TDP of V100 GPU is the same as that of P100 GPU. NVIDIA announced the A100 GPU in May 2020. The A100 GPU is based on the Ampere architecture. The peak FP32 performance and TDP of A100 GPU are 19.5 TFLOPS and 400 watt respectively. The most notable aspect with respect to manufacturing viability is the difference in process technology. As summarized in Table 2, the P100, B100, and A100 GPU are manufactured using different process technologies. In general, manufacturing viability increases as the process technology advanced. Therefore, it's expected that more advanced GPU generation will exhibit larger performance and power efficiency variations. In addition, it's expected that differences in power consumption between A100 GPU will be larger than those exhibited by P100 and V100 GPU because the A100 GPU consumes more power than the other GPU considered here. We use a variety of single GPU programs selected to the benchmark suite for our experiments shown in Table 3. We use 22 benchmark programs in this study. We select 6 programs from across the sample to test primitive operation on GPU. 10 programs from Rodinia 3.1 benchmark suite are used as computer-intensive workload. 6 programs from the Power benchmark suite are used to test more diverse workload. Because individual kernel functions within a program have their own performance and power characteristics, the analysis is per kernel. For this, we extract 48 kernel functions from the 22 programs and execute them on each GPU. All programs executed on Thermal 3.0 are compiled with CUDA toolkit 10.0.130, while all programs executed on Flow Type 2 and Wisteria-A are compiled with CUDA toolkit 10.2.89. We execute each kernel function 40 times to reduce impact to latency variation. We use the NVIDIA System Management Interface for power measurement. This interface, which is included in the CUDA toolkit, is a command line tool for analyzing CUDA program running on GPUs. Executing the command NVIDIA SMI on a host GPU enables us to monitor various states within a GPU during the execution of the program. The command NVIDIA SMI has many options for correcting the GPU state. We use the 4 options listed in Table 4 in our experiment. Repeating NVIDIA SMI with the option produce time series data of the power consumption of a GPU. With this data, we compute the average power consumption of the GPU running a kernel. We repeat NVIDIA SMI at 1 millisecond interval. We measure the CUDA kernel performance from host code. To measure per kernel power consumption of GPU, we have to execute kernel individually. For this, we insert the function CUDA device synchronize after kernel run to wait for the completion of kernel execution. We also use manual timer to map timestamp reported by NVIDIA SMI to interval during kernel execution. More specifically, our timer function reports two wait times before kernel launch and after synchronization. We regard that the kernel running on GPU when the timestamp reported by NVIDIA SMR are included in the duration between the above two times. Because GPU perform differently and consume different amount of power depending on their generation and running kernel, the performance and power profile have quite different distributions. A direct comparison of the variances or standard deviations of the dataset is inappropriate for different distributions. So we use the coherent variation CBA instead. The CBA is commonly used to provide a reasonable comparison of multiple distributions. Figure 3 shows the average CV of the total average power consumption of the GPU in three systems. The total average power consumption of GPU was computed by averaging the average power consumption during the execution of kernel overhaul runs. This operation creates the same number of data points as the GPU count for each kernel. From these data points, we compute the CV of the total average power consumption of the GPU for each combination of systems and kernels, and then computed the average CV for each system by averaging the resulting CV over 48 kernels. The horizontal axis represents the GPU generation, and the vertical axis represents the CV. The figure shows that the float type 2 has a larger variation in GPU power consumption than Tsubame 3.0 as expected. On the other hand, the figure shows that Wisteria-A had smaller variation in power consumption in the GPU than float type 2, contrary to our expectation. Because TSMC doesn't disclose the degree of variation in each process technology, it's difficult to identify the source of this inversion. However, we believe that the EUV lithography used in the TSMC 7nm processing may contribute to a reduction in process variation. To support our claim, we will evaluate power efficiency variation in another type of processor manufactured by TSMC 7nm. Figure 4 shows the relationship between the average power consumption and the CV of the GPU in three systems. The horizontal axis represents the median power consumption of GPU and the vertical axis represents the CV. The plot represents the kernel executed on the GPU. The figure shows there are fewer adrenal in the kernel, and many CV are between 0.02 and 0.05. The figure clearly shows that the three systems have different trends in terms of power efficiency variation over kernel type. With more power-hungry kernels, the P100 and A100 exhibit smaller variation in power efficiency, while the V100 GPU have larger variation in power efficiency. This is because the variation in static power consumption is the dominant form of the power efficiency variation for P100 and A100 GPU, whereas the variation in the dynamic power consumption is dominant in the power efficiency variation in V100 GPU. Figure 5 shows the average CV of the execution time for the GPUs in the three systems. As shown in the figure, the average CV of the execution time increases gradually as the GPU generation advances, but the differences are very small. For example, the difference in the average CV of the execution time between float type 2 and Wisteria-A is about 0.001, which is 1/10 of the difference in the average CV in the total average power consumption between these systems. Figure 6 shows the breakdown of CVs of kernel execution time in three systems. The figure shows that many kernels show small variation in performance of GPU. Specifically, 81 to 94% of kernels shows the CV less than 0.01. A few notable kernels show significant variation in performance of GPU, but overall we can say that GPU have a little performance variation in no power and frequency capping scenario. Figure 7 shows the power consumption of 256 GPUs in Inspiron 3.0. The horizontal axis represents the kernel, and the vertical axis represents the power consumption of the GPU. The top, middle, and bottom lines of each box represent the 75th percentile, median, and 25th percentile value in the dataset of 256 data points, respectively. Each of these data points correspond to the total average power consumption of a GPU. The maximum and minimum value in the dataset provide the endpoints for the whiskers. Some outliers represented as circles are excluded from the dataset. The kernels are sorted in descending order of the median value. The figure shows that the 256 GPU in Inspiron 3.0 exhibit significant differences in power consumption for some kernels. For example, there is a difference of up to 71 Watt for kernel GPU CUDA, considering a difference of up to 30% in power consumption of CPU. We think that a difference of 71 Watt or 25% over maximum power consumption in Inspiron 3.0 is reasonable. Figure 8 shows the power consumption per GPU for 4 kernels that have distinctive features. The horizontal axis represents GPU, and the vertical axis represents the power consumption. The top figure shows the cases where the GPU are sorted in descending order of the median of the average power consumption during the execution of a kernel GPU CUDA, while the bottom figures shows that the cases where the GPU are sorted in descending order of the median of the average power consumption during the execution of a normalized red kernel. Each box plot represents run-to-run efficiency variation on GPU. The figure clearly shows that these kernels can be classified into two groups. One is the kernel with high power consumption, kernel GPU CUDA and black scores, and the other is the kernel with low power consumption, scan into two kernel and normalized red kernel. The first group of kernels shows that the power consumption of GPU drops to the right in the top figure, while the second group shows that the power consumption of GPU drops to the right in the bottom figure. This means that dynamic and static and/or memory power consumption of GPU have different distribution in power efficiency variation. Therefore, different set of GPUs are power efficient or inefficient for each group of kernels. As shown in Figure 9, the 256 GPUs consume a different amount of power for kernel GPU CUDA, which is the second most power-hungry kernel in our benchmark program. For example, the most power-efficient GPU consumes a median of 212 Watt, whereas the least power-efficient GPU consumes a median of 283 Watt. The difference in power consumption between the best and worst GPU is 71 Watt, which is greater than the difference of up to 24 Watt between runs. Thus, the power efficiency variation across different GPUs are not negligible. Figure 10 shows the performance variation across 256 GPUs in Inspiron 3.0. The horizontal axis represents CUDA kernel, and the vertical axis represents the execution time. The figure shows that the 256 GPUs in Inspiron 3.0 have a relatively small difference in performance when compared with the power efficiency variation, though they have a larger difference in performance between kernels. Many kernels produce small variation in GPU performance, and there is little difference in the degree of variation. For example, there is a difference of 0.02 seconds between the best and worst GPU for matrix small CUDA, which is 0.994% of the execution time on the median GPU. A few kernels exhibit slightly large performance variation across the GPUs. For example, normalized weight kernels show a difference of 0.23 seconds between the best and worst GPU, which is 8.3% of the execution time on the median GPU. These kernels are highly influenced by variation in the number of operations associated with dynamic thermal management system and timing variation in texture and constant memory access and thread synchronized operations. Figure 11 shows the power consumption and clock frequency of a GPU during the execution of Kubernetes gem. As shown in the figure, the GPU often hits the power thermal limit and reduces the clock frequency during the execution of Kubernetes gem. As a result, this kernel produces quite a different execution time between GPUs. Figure 12 shows the performance of top two kernels that show large performance variation on the GPUs. The difference in execution time between GPUs is greater than that between runs in the case of normalized weight kernels. Therefore, we can say that this kernel has performance variation on GPU clearly. In contrast, the difference in execution time between GPU is comparable to that between runs for CUDA initialized variable. Because CUDA initialized variable has a shorter execution time than the other kernels, it may be more strongly affected by run-to-run performance variation. Figure 13 shows the power consumption of 240 GPUs in flow type 2. The kernels are sorted in descending order of the power consumption of the median GPUs. As shown in the figure, these 240 GPUs in flow type 2 exhibit significant differences in power consumption for many kernels. For example, there is a difference of up to 60 watts for kernel GPU CUDA. Figure 14 shows the performance variations among 240 GPUs in flow type 2. The figure shows that the 240 GPUs in flow type 2 have relatively small differences in performance when compared to the power efficiency variations similar to 2.0. For example, there is a difference of 0.02 seconds between the best and worst GPU for kernel GPU CUDA, which is 0.67% of the execution time on the median GPU. A few kernels that are highly affected by operations associated with dynamic thermal management system and memory access exhibit slightly larger performance variation among the GPUs. For example, ink kernel shows the difference of 0.11 second between the best and worst GPUs, which is 7.6% of the execution time on the median GPU. However, most kernels have small variations in performance among GPU in flow type 2. Figure 15 shows the power consumption of the 360 GPU in Wisteria-A. The kernels are sorted in descending order of the power consumption of the median GPU. As shown in the figure, the 360 GPU in Wisteria-A have significant differences in power consumption for some kernels. For example, there is a difference of up to 16 watts for binning kernel. Figure 16 shows the performance variations among the 360 GPUs in Wisteria-A. The figure shows that the 360 GPU in Wisteria-A have relatively small differences in performance when compared with the power efficiency variation as for 3.0 and for type 2. For example, there is a difference of 0.02 seconds between the best and worst GPU for Kubernetes system, which is 0.94% of the execution time on the median GPU. A few kernels that are highly affected by operations associated with memory access show slightly larger performance variation across GPU, similar to flow type 2. For example, ink kernels shows a difference of 0.32 seconds between the best and worst GPUs, which is 80% of the 80% of the execution time on the median GPU. However, many kernels have small variation in performance among the GPUs in Wisteria-A. In this study, we analyzed the impact of different GPU generation and kernel type on the performance and price variation among GPUs. Our analysis using 3 generations of GPU and 48 CUDA kernel illustrated that both the GPU generation and kernel type had a significant impact on the power efficiency variations of GPU. We also showed that several kernels produce an attractive feature in performance variation on GPU, although many kernels exhibit small variations. In future work, we will investigate the performance and power efficiency variation among GPU in a more practical scenario using real HPC application. In particular, we will test the multi-GPU workload because some real HPC applications are executed across multi-GPUs, and the experimental results presented in this paper suggest that a variation area job scheduler is needed to increase the energy efficiency of GPU-based production systems. Therefore, we will develop such a scheduler in the future, including a variation area GPU power model. Thank you for listening.